For more than half a century, one single material has been the engine of pretty much all human progress: silicon. It's what built our modern world. But what happens when that engine starts to fail? All right, let's get into it. You know, this isn't just a clever metaphor. The relentless march of silicon technology, the very heartbeat of our digital age, is slamming into fundamental physical limits. The engine is quite literally sputtering, overheating, and on the verge of breaking down. For 50 years, Moore's law was the rule the entire tech world lived by. It wasn't really a law of physics, but more of a self-fulfilling prophecy. And it gave us everything from supercomputers down to the phone that's probably in your pocket right now. The big problem? That prophecy just isn't coming through anymore.
So the issue isn't just about money anymore, even though new chip factories cost like $30 billion. No, now we're crashing headfirst into the hard limits of physics itself.
And here's where it gets really fascinating. These three walls, they're all connected. First, you've got the power wall. As we shrink transistors, they start to leak electricity, like a faulty faucet. This generates so much heat, they're in danger of literally melting. It's the reason your laptop fan spins up like a jet engine, and why chip speeds haven't really gotten much faster in a decade. Then there's the quantum wall. At this tiny scale, electrons start to do weird quantum stuff, basically ghosting right through solid barriers they shouldn't be able to cross. This means the off switch is never truly off, causing errors and, you guessed it, even more power drain. And finally, you hit the traffic wall. The billions of microscopic copper wires connecting all these transistors are creating a huge information traffic jam. The delays are becoming a bigger bottleneck than the actual computing.
The really crucial thing to get here is that when that predictable path of progress just stops, it creates a vacuum. And this uncertainty isn't just a headache for engineers. It's an opening on the world stage. It's a chance for the rules of the entire game to be completely rewritten.
So, this physics crisis basically sets up a brand new geopolitical board game. And on this board, there are a few key squares that give whoever controls them an incredible amount of power. And really, there are two choke points that matter more than anything else. First, the toolmaker, a Dutch company you've probably heard of called ASML. They have a total monopoly on the mind-bogglingly complex EUV machines. They use extreme ultraviolet light to etch circuits that you absolutely need to make cutting-edge chips. And second, you have the master builder, Taiwan's TSMC. They're the artists who use those tools to make over 90% of the world's most advanced chips for companies like Apple and NVIDIA. Just to give you some perspective, a single one of ASML's machines, we're talking about something the size of a city bus, costs $380 million. That alone creates a financial barrier to entry that is almost impossible to overcome.
And that 90% number? That's the key to TSMC's power. See, even if you could afford the machine, actually perfecting the manufacturing process is an art they've mastered over decades. It gives them near total control over advanced chip production. So recognizing this immense leverage, the United States made a really decisive move. It used its influence over these choke points to effectively cut China off from the future of silicon, banning the sale of the most advanced tools and tech.
And the impact was immediate. It was severe. Even the CEO of ASML himself admitted the move was, quote, profoundly effective. He estimated it set China's own chip industry back by maybe 10 to 15 years.
So, what do you do when you're completely blocked from winning the game? Well, you don't keep playing by the same rules, right? The most logical response is to just flip the entire table over and start a totally new game, one with completely different rules.
And China's new game? It's not about trying to catch up on silicon. It's about replacing it entirely with a material that's been nicknamed the golden semiconductor.
This new material is called indium selenide, or InC, and it seems almost perfectly designed to solve silicon's three big problems. For electrons, silicon is like a bumpy country road. InC is a frictionless superhighway, which means much faster chips. When it comes to interacting with light, silicon is like trying to throw a ball into a moving basket. It's super inefficient. InC is like throwing into a stationary one, which makes it perfect for combining light and electricity on a single chip. And this property doesn't just cut down on power leakage, which tackles the power wall, but it could also allow for light-speed communication right on the chip, which would completely solve the traffic wall.
Now, for years, InC was just a lab curiosity. It showed promise, but it was impossible to make at any real scale. That all changed very recently. Building on the whole 2D materials revolution that started with graphene back in 2004, researchers in China announced a major breakthrough, a new way to mass-produce high-quality 5-centimeter wafers of InC. This was a huge signal that their goal isn't just about science, it's about building a new industry.
So this breakthrough is the foundation of an incredibly daring bet. We're talking about a high-risk, high-reward strategy to remake the world's most critical industry basically from scratch.
This is a classic leapfrog strategy. Instead of trying to catch up in a race where you're already miles behind, you try to jump clear over the leader by betting on a brand new technology. China is basically trying to make the West's total dominance in silicon completely irrelevant by changing the material the game is even played on.
But, and this is a huge but, the challenges are monumental. This chart really puts the task into perspective. The Chinese breakthrough produced a 5-centimeter wafer. The current industry standard for silicon is 300 millimeters or 12 inches. I mean, scaling up production by that much is just a staggering engineering challenge.
And the economics are just as daunting. Silicon is the second most abundant element on Earth. It's practically dirt cheap. Indium, on the other hand, is about as rare as silver. On top of that, you have the entire silicon ecosystem, built over 50 years with literally trillions of dollars of global investment. The ecosystem for InSay, it's pretty much at zero right now.
You know, the biggest risk here isn't just that it might fail completely. It's something called a Pyrrhic victory. China could spend hundreds of billions and successfully dominate a tiny, niche market for special InSay chips, while the rest of the world's multi-trillion-dollar economy keeps chugging along on silicon. That would be a massive strategic loss.
So that leaves us with the big question. Is this the start of a new tech empire, one built on a so-called golden semiconductor that will fundamentally shift global power? Or is it a fantastically expensive distraction from the real game, which is still being played on a board made of good old silicon? The race is on, and honestly, the outcome is going to define the next 50 years.